All right. Last time we talked about simple interest. So I think it lives up to its name, but thanks to that simplicity, it doesn't really come up all that often in applications. More often than not, you're going to be dealing with an investment or a loan scenario where interest builds up over time and then starts building interest of its own. So that's what we generally call compounding interest, and that's what we're going to be looking at right now. As it turns out, in terms of calculating the interest directly, that's not usually the way we go at it. That could be a bit of a hassle. Instead, we generally go about calculating that future value that we talked about last time. And as you can see in the notes file posted for section 6.2, our standard future value formula, if we're compounding once a year, looks like this. I wrote T. The notes file uses N. That's not a bad idea. So R here being an interest rate, again expressed as a decimal rather than a percentage. P, principal, the amount we've invested. It could also work for borrowing if you weren't making any payments for some reason, I guess. And N is the number of years you let the investment sit, essentially. So we have an example where we're given, we put away $3,000. So we have a P of 3,000. We're getting an 8% annual interest rate. So R is 0.08. And then we're told we want to know what the future value is 5 years after we make the investment. So N is going to be 5 in that instance. So we fill in the blanks. So we have 3,000 times 1. I normally am not going to write 1 plus 0.08. I think we can all safely add those two together and just write that as 1.08. If you need to, it's okay, I get it. But as you've seen, I don't have a ton of board space to work with, so I'm going to try to save it where I can. And then we need to take that 1.08, raise it to the 5th power. So again, if you're using a calculator, you've got the exponent key, that kind of thing. We used it a lot last chapter, so hopefully you're on board. Anyway, so we work this guy out, and to the nearest cent, I got the following: $4,407.98. So there's my future value. So 5 years down the line, that's how much is sitting in the account. We're also asked to work out the interest here. So we actually kind of need to manipulate that future value equals P plus I formula a bit. But so basically, if you want to figure out the interest, well, we can subtract whatever we initially put in here away from our future value. So S minus P in this instance. So the 4407.98 minus the $3,000 we put in there to begin with, and that's 1407.98. Okay, so that's annual compounding. So that comes up in some scenarios. All right. The bigger and more often, as you're saying, I think more regular occurrence here is not necessarily on an annual basis. Most investments, they build up like monthly. So if you have an account that's, building interest, you'll often see some interest every monthly statement. Some investments may also have quarterly, compounding, that kind of thing, where every, quarter of the year things roll in. So in that instance, we're going to be using periodic compounding rather than annual compounding. In practice, it turns out you don't really need to change the formula that much. So, as you notice, there's a formula that writes it out in terms of annual and then the number of compounding periods per year. I think most students find it easier if they kind of break this into chunks. And by determining this thing I, that we call the periodic interest rate. If you look at, say, like a credit card statement, they'll usually have some kind of daily periodic rate or something like that factored onto, a statement to talk about, how they're, applying, interest to your balance. So in here is no longer going to be a number of years, it's going to be a number of compounding periods. So you'll notice the formula there has like M for the number of times it happens in a year, and then you multiply that by the number of years if you need a number of compounding periods. I find it beneficial in most instances for students to work out the values for I and N separately based on the setup of a given problem. As if on Q, we've got an example sitting there that says, if we tell you you have an annual interest rate of 15%, we're rolling the interest in quarterly over the course of 4 years. We need to work out the value for I, our periodic interest rate, and how many compounding periods we're going to have by the time it's all said and done. So we're given an R of 0.15, and let's see. We're told it's being done quarterly. There's 4 quarters in a year. Shouldn't have written that M, but the number of years we let the investment sit is also 4 years. So to get I, we take our 0.15 annual rate and divide it out, by the 4 quarters that we have in the year, and we get a periodic rate per quarter of 0.0375, or 3.75% if you want to go there. In the number of compounding periods, we just take M and T and multiply them together. 4 times 4, that gives me 16. Okay? There's another problem in the notes file. I'm leaving that for you for an assignment that you'll see in Moodle later. Let's go ahead and take a look at the next example where we actually use this to do something for us rather than simply cranking out I and T, I and N on their own. So for the record, we're going to be calculating I and N a lot as this goes on. So you'll have plenty of practice with this by the time it's all said and done. All right, so the next example that I want to take a look at skews in a slightly different direction. So it says we want to have $24,000 on hand in 3 years. Given a particular interest rate of 6% and compounding happening semi-annually, so for the record, semi-annually is twice a year. So we want to know how much we have to put aside. So instead of looking for the future value S, we want to find the principal P. So in this case, we know that our S is 24,000. We need to work out the I and the N in order to deal with this. I could write out the R and M and T values, but I'm going to go ahead and work this all together at once. So my I in this case is that 6% interest converted into a decimal, like you do, divided by the number of times we're rolling the interest in each year, which is 2. So we have an I value of 0.03. And so then we'll have an N value. We're letting it sit for 3 years. So we have 2 compounding periods per year times 3 years. That gives me 6 total compounding periods. All right. So filling in our S value in this formula right here, that's our 24,000. We don't know P. 1 plus I is 1 plus 0.03, that's 1.03 to the 6th. And to get P by itself, our usual algebraic song and dance, divide both sides of our equation by this thing. If you wanted to have it worked out, that's fine. So we have 1.03 raised to the 6th power in the bottom of the fraction. And the principal I came up with in that instance was $20,099.62. So that's an example of periodic compounding where we've actually used this to work out how much money we got to put away. So that's kind of a practical type question. There's one more problem in here I want to take a look at before we shift gears. So the next example takes a slightly different tack, and in order to get a complete solution, we kind of have to go off to the side from some of the other stuff that we've done. I promise we'll get through it. So it talks about if we put away a certain amount of money in whatever the Sagamore Capital Opportunity Fund is. Real talk, I have no idea what that is. I'm going with the problem that's provided. Then 10 years later, essentially, we've got lots of dates in there, but it really boils down to if we let it sit for 10 years, we have, that 10 grand turns into 46,649 and 55 cents. And we want to try to figure out the interest rate. And the good news is this time around it's annual, so I and R are really going to be the same thing for us. That's nice when it's on an annual scale. So in this last example, we've got, let's see. The future value was the 46,649.55. We got 10,000 over there. 1 plus r. We can't really do anything else with that at this point. We've got this to the 10th power. We'll see how to deal with that in a moment. So we divide both sides by 10,000. So dividing 10,000 here, it goes poof. Over here, if we divide by 10,000, that's just going to move our decimal point 4 spaces. 1, 2, 3, 4. So 4.664955. You'll notice I generally don't round anything until I get to the bitter end. So now, technically, I guess you might try to do this with logarithms. We saw stuff like that before, but it turns out we don't really need to in this instance. To get rid of raising something to the 10th power, we can do what's called taking the 10th root. So it feels kind of weird to write that. We did that with the cube root back in chapter 5. You can interpret this as raising this number to the 1/10th power. This is something that we need to do like this time and maybe once more, like on a homework problem in the entire semester, so don't stress too heavily about it. So to get r by itself from here, it's a matter of subtracting 1 from both sides. For the record, yeah, taking the 10th root of this is going to bring it down pretty fast. So when I worked that out, I got an r value of approximately 0.1665. If we convert that into a percentage, which we probably want to do, it's going to look like 16.65%. Okay, so that's one mode of looking at compounding. There's another one that's coming up afterwards. We've actually already referenced it a time or two in the stuff in chapter 5. We'll take a look at that one in just a moment, or however long it takes you to click on the next video.